Okay, hello. Hello. This will be our second Sunday review. I got a special request today for to do heaps and priority queues. I can't I'll be traveling home, so I can't do the Sunday review, so I just provided a video for you guys. Okay, so the priority queue. So a priority queue is essentially a abstract data type. That means that we can implement it in different ways. And in the lectures, you saw insertion sort and selection sort being used to implement priority queues. So the main motivation of a priority queue is that say we have a long list of queues, right? So just like a printer, we have a long list of pages that we need to print out and we don't know which one to print out first. And usually in a queue, we want to do first in, first out. But let's say we have a 100-page queue, a 100-page order in the queue. That means that the one pages will take it would take the one pages printing a lot longer to print out because it has to print all 100 pages first. Essentially, it just slows things down. It's really bad for scheduling to just like do first in, first out, and then just leave it as that. So we want something that can help us prioritize certain like orders or jobs inside the queue so that we don't like hold up scheduling, but the 100-page job will eventually get done. And that usually is done using a binary heap. So the advantages of the binary heap is that its structure, it has it's a complete binary tree, which means it has a two nodes, which is said right here. I don't know why I wrote it, but um it can actually be represented as an array, which is kind of unique for this part, as well as it has, since it's a complete binary tree, that means each level has essentially 2 to the h plus 1. So it's like kind of balanced, but not exactly. We wouldn't use the word balance here, and I'll show you why later. But so the min heap, there's different types of heaps, binary heaps. So the min heap keeps its smallest element at the root. So the one you're seeing in here, the one you're seeing on the right is a min heap. The smallest element is at the root. And then the max heap does keeps its maximum element at the root, and then everything under it will be less than it. And then each subtree of a binary heap is also a binary heap. So that just means that it has two nodes, its height is 2 to the h plus 1, and then its root node is either a min or max of the nodes under it. Okay, so this is the representation of it as an array. So this is actually pretty important because what this shows you is, so 13 is here, 21 is here, 16 is here, 24 is here, 31, 19, 68. So if you look at this, there's like multiple things you can point out. So the first thing is the root node is the first node, right? Its two children's are 21 and 16, which are there, but it's also that they're also on the same level. They're also left to right. So this is from left to right on the same level. Okay. And then we can also go down to 24, 31. So we see 24, 31, 19, and 68. So these are also on the same level. They also go from left to right. And we can also, so essentially, what that means is that if we know they're all on the same level and we all know they go left to right, and at each level there's 2 to the h. Um, so at the first level it's 2 to the 0, 2 to the 1 nodes, and then 2 to the 2 nodes, right? So that just means that we can actually find out the parent of any node in the array. So the parent of 24, we would look here. So the parent of 24 has an index of 4. I don't know the equation off the top of my head. Oh, it says right here. Yeah. So this is the equation, 2 to the I and 2 to the I plus 1. Essentially, we can find the parent of 24 and it will essentially be 21. And then 31 will also point to 21. So it's just a really fast way to find the parent. That's why you usually want a array type of implementation for a binary search tree. Right? Okay. So inserting. Inserting will you'll try to place the node at the next available place, and then you'll perform upheap. So upheap is the key thing here. And I'll show you what upheap is, but this will eventually end up in O of log n times. So that one seems pretty simple. So looking at this tree right now, before it has 14, we want to place 14 at the next available spot. So the next available spot will always be from left to right. So left to right at the very bottom level and on a leaf node. So the next available node will be this one. Okay, so this is where we put 14, and we have to perform upheap, which upheap is honestly really simple. All you have to do is compare the top and the bottom and say that is the parent greater than the child of the inserted node. And if that's true, then we just need to move it up. So 14 is now, and then 31. Okay, and then we see these two. So is 21 greater than 14, which it is, because this is a, does it show here? Yeah. Because this is a minimum heap, we want to keep all of the smaller nodes at the top. So it moved 14 up here, as you see right here, and then 13 is not smaller than, or 14 is not smaller than 13, so you don't have to move anywhere. That's upheap. And notice how at each level, the number of possible nodes is essentially log 2. So that's just like kind of like the height of the tree. Okay. So removing. So the removing min max is actually the part that makes a priority queue makes a binary heap, or no, makes a priority queue implemented by a binary heap. So essentially the only remove operation you'll need is remove minimum or remove max. So the reason why is like the whole part of this data tree is that the minimum will always be at the top and the maximum, and then it'll keep those properties as it inserts or deletes anything. So those properties are honestly really important to keeping the just like the tree and implementing a priority queue. Okay, so we're gonna delete the root node, and then we're gonna replace it with the last node, and then we're just gonna perform down heap. So up heap is done for inserting, down heap is done for removing. Okay, so let's see, we want to remove the minimum, so that means we have a min heap right now. So 13, we need to remove the root, remove root, and then let's look at our lowest node. So our most our um What's available node? So essentially it'd be 31. So this is our very last node. So it goes from left to right and then like the bottom level as well, similar to how you did the insert, but instead of inserting, we go for deleting, which means we had to take this one and then we replace it up here. So that's what they mean by delete and then replace. And then we see that we have to do perform down heap. Remember how up heap we had to check like here to here to here to here? Well, because now the lowest element is at the top. We need to move it down. So we want to check here to here and then sorry, and then check here to here and then essentially oh, I think they moved it down to the left. Actually, yeah, they moved it down to the left. So they went here to here and then they said that because 26 is less than 31, we check here to here. Okay. So I believe for the most part, if both of your children nodes are smaller than the parent, you usually go to the left. I think it's usually defaulting to the left. I don't know if there's a different case that there is, so I'm not completely sure about that. But the reason why you just go to the left is because you always want your left you always because we're removing a node, right? You see how 31's right used to be right here? That means that there should be one less node in the binary heap, and that means that we shouldn't be putting a child here, right? But if even if we do either way, it should keep the binary tree property, binary heap property, yeah. So 31, and then let's just double check this. So our root node is smaller than our two um children nodes, and then those children are smaller than their children nodes as well. Okay, so the priority queue leak code question. I'll just go through this one pretty fast. We also did through lab, so you guys for the most part should know the answer by now. But essentially, we want to find the kth largest element in a sorted order. Or it's actually, yeah, sorry, it's not sorted. So the array is not sorted, but the easiest way to get it is by doing it in a sorted order. And then can we solve it without sorting essentially? So can we solve it because sorting is essentially O(n) squared. That's like because like it's insertion, deletion, or and it's insertion sort, selection sort, and then I guess there's also like merge sort and quick sort, but essentially, we can prove that there's a faster way, right, to solve this, and then that way is priority queues, implemented by minimum heap. So, the reason why when use a maximum heap is because the maximum heap would give us a different number than we're looking for. So what we want is a um so what we want is the kth largest element. So let's say our tree this is our and then k is equal to 30. And so we want which element? So the third largest element. So that would be 4. And because the maximum heap, the way they store it is the maximum will be at the top and then the children will be at the bottom. But the children aren't always guaranteed to be in order. So these two don't have to be in order. And because they don't have to be in order, it actually doesn't mean that we know which one is the third largest element. We just know the third largest element is on this row, right? So the only way we can do that is using a minimum heap. And a minimum heap, I don't want to go through the code or anything. So I just like draw it out for you. But the minimum heap essentially helps us tells us not only the largest element, but the way we can make the minimum or heap is the kth largest element is we make a minimum heap the size of k. So k is equal to 30, so we make a heap the size of 30. So that would be like this. And don't assign any numbers for now. Then we'll go through three elements in the heap and then we'll just insert them. 3 and 4. Okay. And then so we're guaranteed to have the minimum element at the top, right? So, because we're looking for the largest elements, we want to see if the minimum at the top is greater than any large element. So, let's check 5. So, 5 right now is larger than 1. So, since 5 is larger than 1, then we want to remove 1 and then we want to insert 5. And then essentially what that look like is some sort of tree that look like here or something. Okay. And then we check 8. And 8 is larger than 3. So we want to replace 3. And then redo the tree. So 4 is the new. And because we have no more elements in the array list, we can prove that this, the minimum element is essentially the largest kth element. Does that make sense? So, that's essentially log n log k. Um, Essentially what that means is we do log k operations to like remove it and then insert it, and then there's n elements. So we have to do remove and add in the worst case for n elements. Yeah, and then your lead task, yeah. Okay. I think that's really it I have for heaps. I think the biggest part is understanding when to use down heap and up heap. So up heap is used for insertion and then down heap is used for removing. And honestly, I um it's easiest to think about it as whenever if you have your larger element at the bottom, that just means that you probably have to do up heap, which is for insertion, and then if you have a element at the top, when after you remove the root and then replace it, then you just need to do down heap. So yeah, feel free to message me if you have any questions about heaps or priority queues. But priority queue is just the abstract data type, and then there are other ways to implement priority queue. So don't, it's not only binary heap. Binary heap is pretty much one of the most used implementation of it just because it's the most efficient. And then there's other you'll probably learn later on what you use a priority queue based on binary heap implementation for, but Dijkstra's, which finds the shortest paths in a graph, is really important in when you implement these priority queues in binary heap. And then it gets a little bit complicated whenever you have different implementations of things. So in Dijkstra's can also be used. The way Dijkstra's is made, you can also implement it using different types of abstract data types, not just a priority queue. So make sure you do know, like I don't think you have to know the exact implementation, but make sure you do know the runtimes and the yeah, just the runtime and time complexities of each implementation from priority queue. So like if you're doing it with an insertion sort, merge sort, binary heaps, there's different runtimes and make sure you just know those. Okay, that'll be it.